Greetings and welcome. Today's lesson is about modeling motion using parametric equations. Alright, so technically yesterday we did talk about parametric equations and motion that was linear, where we had an object that would move along a linear path over time at a constant rate. Alright, and we were able to locate that. We had an equation for x, the horizontal motion, and y, the vertical motion, all defined based on a parameter called t. So today we're going to talk about a different type of motion, specifically projectile motion, which will follow the path of a parabola, which you're probably familiar with. And you've probably done work with parabolas before, right? And parabolas have all sorts of different behaviors. They are, first of all, symmetric, not this little parabola that I just drew. They have a maximum value, which is on that axis of symmetry. The time it takes for an object to go up is the same amount of time it takes for it to land, or to go down, rather. At the peak, the vertical motion is 0. It actually comes to a stop, vertically speaking, and then starts to accelerate on its way down, and things like that. So we're going to be talking about parabolic and projectile motion, I guess, is how I describe it. But before we get there, I want to talk about velocity. All right, velocity is a vector, and it has direction and magnitude. The magnitude describes kind of the speed of the object, and the direction would be described by an angle. So imagine I have an object that is launched at an angle theta, all right, at an initial velocity. So I'll call that vector v. All right, so the length of this vector would be the magnitude of vector v, but this vector itself here we'll just call vector v. And so even if I'm talking about a projectile, right, whether I'm shooting from a cannon or kicking a soccer ball, or shooting an arrow, whatever the case may be, it has an angle and initial velocity. All right, and that mathematically could be more difficult to find depending on what your situation is. If you have high-speed cameras or stuff like that, then you could try to figure these out, which is what kind of like the Mythbusters do. But let's assume that we're able to determine the initial velocity, or the muzzle velocity of our object, if we're talking about a gun or something like that, and the initial angle that it's at, because the angle is going to change over time. It turns out it will be valuable to us to be able to break this down into the horizontal and vertical components. All right, so, and we've done this practice before. So this I'll call the horizontal, velocity, and the vertical velocity. And these are technically also going to be the initial velocities of these things. So this is initial velocity. All right. So this velocity is going to change over time. It's going to change direction and speed, or magnitude. The vertical velocity is going to change over time. At some points it's going to be going up, it's going to get slower and slower and slower, and then later it's going to actually be going down. So this velocity changes over time, but the initial velocity we can still calculate. And it turns out the horizontal velocity, at least ignoring wind speed and friction and whatever, the horizontal velocity actually can be constant, at least until it hits the ground, right, and starts slowing down because of bouncing or rolling or whatever. So the horizontal velocity can be constant because it's not affected by other forces, unless we, like I said, include wind speed. The initial vertical velocity is affected by gravity. All right, so that's the thing that's going to be causing this vector to change over time, is gravity. So if I wanted to figure out what either of these velocities were, or more specifically their magnitudes, you could actually find the horizontal velocity, or initial value, using some of our basic trigonometry, right? So if I know the initial magnitude and the angle, I can actually figure this out just using trigonometry. Here's adjacent and hypotenuse. So cosine of theta would be Vx over V. So I could solve for Vx or specifically the magnitude of Vx, and that would just be the product of the magnitude of my initial velocity vector multiplied by the cosine of theta. And we've seen, like I said, we've seen that before. And the vertical initial velocity will be similar, except this is the opposite, that's the hypotenuse, so it would be related to sine. So the magnitude of the initial vertical velocity, right, is going to equal my velocity vector multiplied by sine of theta. Okay, so using these, we're going to actually do our first example where we're going to just figure out what the initial horizontal and vertical velocities are for this problem. So let's do this little example here. And it says, find the initial velocity and initial horizontal velocity and vertical velocity for a stone. I don't know why you're kicking a rock, but apparently that's what we're doing. Kicked at with an initial velocity of 16 feet per second. All right, so that is speed, right? And at an angle of 38 degrees. So now that I have a direction, I actually have a vector I can describe. So 38 degrees, let's say, is like that. 38 degrees. And 16 feet per second. Right? So if I want to break this up into find the Vx and Vy, so to speak, I can very easily do that using the little formulas I had a moment ago. So Vx is just going to equal 16 times the cosine of 38 degrees. So that is going to equal, let's see, make sure I'm in degree mode here. 16 times the cosine of 38 is 12.608. So, and this would also be measured in feet per second. All right. So even though the object is initially traveling at 16 feet per second in this direction, it's not going to continue doing that, and it actually is traveling 12-ish feet per second horizontally speaking. All right, and it would continue to do so if that was somehow uninterrupted. All right, and then the vertical, actually I forgot to throw the magnitude symbols around this, didn't I? Then the vertical initial velocity is going to equal 16 times the sine of 38 degrees, right? So that's going to equal 16 times sine of 38 degrees is about 9.85 feet per second, right? So that is the magnitude of the initial vertical velocity. And like I said, over time, gravity is going to slowly be eating away at this, so to speak. Now, if I wanted to make these parametric equations, all right, and if I wanted to introduce a variable representing parameters, what I could do is actually throw a t in front of those, is what we're going to end up doing. But first, I want to actually show you this picture of what a projectile parametric would look like. All right, so here's the path of an object. The black dot is where it is at different times. So you can see that, and it has the green vector is the path of the object and the velocity of the object. So it's vector at any given moment. So you can see that it's actually changing over time for the green vector, right? So this would be the initial velocity, and here's theta that we've been talking about. And then the blue vectors are talking about the initial horizontal velocity. And notice that the blue horizontal vector is actually the same constantly. It never is not the same, right? Because we're assuming no wind speed. But the vertical vector, all right, it has an initial starting value, and it's actually getting shorter, shorter, shorter until it's nothing. All right, it's a 0 vector there, and then it starts going down, 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 down. And I'd want to point out that this would technically line up with this if I had one exactly across from it. I guess this one, arguably, yeah, those are the same height. So that the speed it was traveling up here is the same speed that it was traveling down here. The speed that it's traveling down here is the same as the speed that it was traveling up there. So gravity was slowly eating away at it until eventually it overcame it and was pulling it down faster and faster. And it landed at the same speed that it started at, assuming no other wind speed or forces were occurring on it. So equations, parametric equations for the path of a projectile. All right, because like I said earlier, yesterday we talked about linear parametric equations. But let's start with this. It says if a projectile is launched at an angle of theta with the horizontal, so right, measured from a positive x-axis, with an initial velocity of magnitude v, the path of the projectile may be described by these equations where t is time and g is the acceleration due to gravity. So here are our two equations. So notice, very similar to the calculations for initial velocity from a moment ago, right? V cos theta, V cos theta. The only addition is this variable t, right, or time, the location of the object over a given time. So this whole V cos theta represents just the initial horizontal velocity, and I'm just multiplying that by time. Rate times time equals distance. So this x is going to be the location of the object t seconds after it was initially hit, right? So this represents the horizontal location of the object, and this is a parametric equation. Now, the vertical is very similar. So v sine theta, that's the initial vertical velocity, that's being multiplied by t. So that if this was uninterrupted, if this next term was not here, that would just continue moving in that direction indefinitely, and we would actually have had a linear path. Okay? However, I've got this minus 1/2 gt squared, and you might recognize that from physics classes. G, it says, is the acceleration due to gravity. Notice that it's subtracting here, so it is slowly eating away at this overall speed. Once this is equal to this, that's when I'm at the peak of my parabola of the path, right? And once this is bigger than this, then it's actually right, moving down at those moments. Actually, wait, I just said that wrong. My apologies. Once this is equal to this, then the vertical location is 0. My apologies. So the displacement, the overall location is back on the ground at that point. So when this is actually half the size of that, that's when it would be at the peak of the parabola. But so these two together would represent the location x comma y of our object at time t. Now, in case you're not familiar with accelerations due to gravity, I'll throw those in here for you. Typically, we work in feet per second squared or meters per second squared. And these are constants for planet Earth at, I believe, sea level. Technically, the acceleration due to gravity is a little bit different at like Death Valley compared to like Mount Everest, stuff like that. But this is the general idea. I can now use these equations and do some calculations with them. So let's do our last example. So let's see, this one's about a football player. And here we are. Oh, I pasted it in the wrong thing. Here we are. So a football player, oh sorry, I almost was going to say a football player is kicked with an initial velocity. Hopefully that is not the case. No, they kicked a football, all right, with an initial velocity of 29 yards per second at an angle of 68 degrees to the horizontal. And then it says, suppose a kick returner catches the ball 5 seconds later. So here's question part A. It says, how far has the ball traveled horizontally, and what is its vertical height at time t? So first of all, I'm going to have to figure out the initial velocity, the magnitude of the initial velocity. They gave it to us in yards per second. I'm going to want this in feet per second. So yards per second being 29 yards per second. I'm going to have to multiply that by something in order to get that in feet per second. How many yards are there to a foot? Well, there is, let's see, I'd want 1 yard compared to, right, 3 feet per 1 yard, because I'd want this set up so that the yards would cancel out. So multiplying by 3, I'd actually get 87 feet per second. Okay, so right, because the yards cancel out, I'd be left with feet over seconds. So here's my initial velocity's magnitude. Theta, we happen to know, is 68 degrees. No conversion necessary there. We're working in degrees here. We don't need to do radians or nothing. And then let's see, what else do I need to know? Oh, g, the acceleration due to gravity, since I'm working in feet per second, which was cued by the yards per second. Technically, I could convert this to meters per second, but no one wants to do that. So I'm going to use the 32 feet per second squared. And the per second squared means that this is an acceleration. So to answer the first question, it says, how far has the ball traveled horizontally? All right, it's part 1. So what I'm going to do to calculate that is just plug it into my formula. So Vx, or actually, sorry, x is equal to t. Now let's see, oh, we got to remember what t is. T in our case, time is 5 seconds, right? So I'm going to have 5 multiplied by the initial velocity, 87, oh, getting a little lag, multiplied by the cosine of 68 degrees. Okay, and this is going to be the horizontal location 5 seconds after the initial kick. So 5 times 87 times the cosine of 68 degrees, I get 162.954 feet. All right, so this is the horizontal location. And then it says, what is its vertical height at that time? So once again, I'll take my values and plug them into my vertical formula, right? So that's 5 seconds in, multiplied by 87. Doesn't like my 87s, that's when it's lagging. Multiplied by the sine, whoa, of 68 degrees. However, I then also have to subtract the 1/2 g, the 32, multiplied by time squared. All right, so notice I'm not squaring the 32, I'm just squaring the 5 here. So this is equal to, let's see, 5 times 87 sine 68. This portion is equal to 403.325 minus 16 times 25 is 400. And so it looks like we're at 3.325 feet. So 5 seconds into, right, the kickoff, right, 5 seconds into the hang time or whatever, it is 162.9 feet horizontally away, and it's 3.32 feet in the air when it gets caught. So that's part A. Let's answer part B, which says, which is going to be using some of the same values that we plug in, but it's got another hypothetical. It says, suppose the kick returner lets the ball hit the ground instead of catching it. What is the hang time, which is defined as the time between the moment the ball is kicked and the time it hits the ground? So my first question for you is, how high is it when it hits the ground? So you would probably say 0 feet. So I'm going to say that I want to let y equal 0 feet. Okay? And for my y equation, let's see, they're asking now for hang time. So this time, actually, I don't know what t is. T is the unknown to us. So I'm going to plug 0 in for y. I'll have t multiplied by the initial velocity, 87, multiplied by the sine of 68 degrees, minus the 1/2 32, that's 16t squared. All right, so I've plugged in what I know, and I want to solve for what I don't know. So what I have here is actually a quadratic equation, right? It's a second-degree equation. It's only got 2 terms. And the way we can solve this, we actually know a handful of techniques. You could solve by, once I simplify this, let's do that first. What is 87 sine 68? Okay, I'm actually even going to flip this all around. Negative 16t squared plus 80.665t equals 0. So, if you're looking at this, what I want to point out is that this is a quadratic equation. You could solve by factoring possibly. In this case, actually, we will. It is factorable through GCF. You could solve by completing the square. You could solve by the quadratic formula. In our case, like I said, this is GCF, or actually, I'm just going to factor out the t, because I don't necessarily know how many times 16 goes into that, and we'll leave it there for now. And actually, this will be more interesting. T is t times negative 16t plus 80.665 equals 0. So I've factored this, and the benefit is now I've got 2 things that multiply to be 0. Therefore, one of them is equal to 0. So either t equals 0 or negative 16t plus 80.665 is equal to 0. This one's already solved. Wait a minute, t equals 0. Let's consider what this means. I just asked the question, how long did it take the ball to get to 0 feet high? Technically, 0 seconds into the kick, right? Before the ball was kicked or left the ground, it was still at 0 feet. So that's what this answer means. That's not the one I'm interested in, but that's the proper interpretation of what that answer is. That's before the ball left the ground, it was at 0 feet, right? So our model actually accounts for that. So we'll subtract 80.665 from both sides. Negative 16t is equal to negative 80.665. Divide both sides by negative 16. Good. Negative over negative is going to be a positive, so I'm at least not in negative time. That would be unusual. So 80.665 divided by 16, I get 5.042 seconds. So it turns out that the ball would land 5.042 seconds after the kick. All right, so the way I was able to do that was I realized that time was going to be unknown to us, and I wanted to know, okay, where, right, where's the ball going to be when it lands? Well, it's going to be 0 feet high, so I plugged in 0 for y. Now, if I wanted to ask some other questions like how high was it at its maximum height, I'll tell you what, bonus question, part C, wasn't even part of the plan. What was the maximum height? And due to the nature of parabolas and my ability to ignore wind, we can actually recognize that half of this time is going to be how long it took to get to the max, right? So that's 2.521 seconds is when it would reach its maximum height. And I could actually figure out how far over it went if I plugged that into my x parametric equation. But I want to figure out how high was it. I could plug that into the y parametric equation. So y is now unknown to me. T is 2.521 multiplied by the 87 times the sine, not cosine, of 68 degrees minus 16 times 2.521 squared. And if I evaluate this, times 87 sine 68, close parentheses, minus 16 times second answer squared, and I actually can get 101.669. So I actually can even answer some questions like that as far as how high it was at a particular moment. And if I wasn't interested in the max height, I technically could answer how high was it, not 7 seconds, it would have been into the ground at that point, according to my model, but 2 seconds in or something like that. But using the nature of parabolas, if you know how long it took to land. Half of that time will give you how long it took to reach its max. So thanks for watching, internet friends. I hope this made sense, and I hope you have a wonderful day. Bye-bye.